Okay, the last example we're going to use for our application of torque will be objects in static equilibrium. By static equilibrium, we mean an object that is at rest will remain at rest. That means it can neither translate, so there has to be no net external force. In addition, we're not going to allow it to rotate at all, so there can be no external torques as well. We're going to consider objects basically in the xy plane, so any forces will be in the xy plane, which means they'll exert torques around the z-axis. Now we get to pick our origin, or where the z-axis will be located, anywhere in the xy plane that we want, because we're going to assume the torque will be 0 around any and all points. So we'll pick our axis to be mathematically convenient. So we'll pick a force that will make the calculation simpler. And we can use these conditions, and there are 3 of them, to find values for up to 3 forces applied on our system. And in this case, for an example, we're going to have 2 unknowns, the 2 tensions and the 2 ropes on opposite ends of this scaffolding. So that'll be our first problem. So we will take a person right here with a mass of 65 kilograms that is located at 1.5 meters from one end. We'll say the platform has a mass of 100 kilograms and the length of the platform is 6 meters. I want to find the tension in either rope. The only forces acting are vertical, so we have the 2 tensions acting up minus the 2 weights pulling down, must add up to 0. We'll use one end, it could be either end, we'll pick this end, for our point of reference, so we'll find the torques around this end right here. T1 does not exert a torque because it's acting at the axis of rotation. T2 will exert a torque, as will the 2 weights. So the torque from T2, which is counterclockwise, is T2 times L, minus this one is exerting, her weight is exerting a clockwise torque, so that's minus mg times x, which is the 1.5 meters, minus mg times the length of the platform over 2, because that's where the center of mass be. We now have 2 equations for the 2 unknowns, T1 and T2. You might want to pause the video and do the math. When you're done, these are your 2 answers, so we can find the 2 tensions. Notice the tension on the rope there, the woman is closer, is higher, the opposite side is lower, so more of the weight will be supported by this rope. Okay, another example we can take is a person now on a ladder. So here we have a ladder that has a mass of 45 kilograms. We're going to take its center of mass not to be the middle, but the center of mass is 1/3 of the way up. It has a length of 12 meters, and it's resting on a building at a height of 9.3 meters. The firefighter right here will have a mass of 72 kilograms and will be at the midpoint of the ladder. We want to find the forces acting on the bottom of the ladder right here and the top of the ladder right here. We will take the top of the ladder to be frictionless, because if we didn't, we'd have 4 forces, 2 normal forces and 2 frictional forces. And we only have 3 equations, so that would be an undeterminable problem. To get a 4th equation to determine what the friction force would be up here, we would have to take into account the fact that the ladder with weight on it and forces on either end cannot be perfectly rigid. It does have to bend. So the strength of the ladder would give us the 4th equation to determine how much friction we would have up here. We're going to ignore that. So we'll take the top up here to be frictionless. All we have is a normal force, the force of the wall. On the ground right here, we have a normal force and we have a frictional force. And then we have the 2 weights, the weight of the ladder and the weight of the firefighter. We will take the bottom of the ladder right here to be our axis of rotation. So again, we have 3 equations we can set up. Some of the forces acting horizontally will be the normal force from the wall minus the friction on the ground. Vertically, we have the normal force from the ground minus the 2 weights, the ladder and the person. And we have the torque around the base of the ladder, and the only unknown force exerting a torque will be the force of the wall, and that's at a height h, so that's its lever arm, and this was actually exerting a clockwise torque. Here, gravity is exerting counterclockwise torque, so in the opposite direction. Person was at half the height. The ladder's center of mass was at 1/3. A is just the distance along the base of the ground, up from the base of the wall to the ladder. Using Pythagoras, we can get that. And again, we have 3 equations and 3 unknowns. Again, you might want to pause and do the math. But here are our 3 answers. Notice the wall and the friction are equal and opposite because those have to add up to get the sum of the force horizontally to be 0. This, by the way, is simply worked example in the textbook. Last problem we want to consider is a boom. We've got a beam at an angle right here, and it's holding up a safe with a rope, and we have a cable suspending it to a wall. And what we want to find is how much tension is there on the cable. And we are given the mass of the safe, the mass of the beam, and the two distances A and B. First thing we do is we draw a free body diagram of all the forces acting on the beam. We have the tension, which is pulling it towards the wall. We have the weight of the rope, which is pulling it down. We have the weight of the beam, which is pulling it down. And the hinge will exert a force both horizontally and vertically. Basically, those two forces we could add up and get the net force from the hinge. We'll break that force into two components. And again, we use the sum of the forces acting horizontally, which is the horizontal force of the beam and the tension on the cable. Vertically, we have the vertical force on the hinge minus the two weights. We'll pick the hinge to simplify the math to be our axis of rotation. And here's the torque exerted by the cable's tension and the two weights, and they're pulling in opposite directions. And again, look back at the diagram to see how these two torques were set up. And again, we have three equations and three unknowns. Here we're actually only asked to find this tension. The rest is fairly straightforward. And here is the solution. And again, this is a worked example in the textbook.